Welcome everyone. I am Dr. R. Perumal, Professor of Chemical Engineering, Department of Chemical Engineering, Erode Sengundar Engineering College, Perundurai. Today we will discuss about design of a heat exchanger. Heat exchanger is the major and important unit operation almost carried out in all the process industries. Whenever a system or a process generates heat, this heat has to be recovered from the system then and there so that the optimum temperature can be maintained. Similarly, when a system or a process requires heat, that means heat to be added, in that case also heat exchanger plays a vital role. Therefore, the heat exchanger is a machine or a device used to transfer heat from one phase to another phase. So, the appropriate design of a heat exchanger plays an important role to optimize the critical parameter of the process. So, in this presentation, we will discuss about the classification of heat exchanger, the advantage and disadvantages of each heat exchanger over one another, and what are the characteristics and parameters to be considered for designing a heat exchanger, and the design equation to be considered for specific heat exchanger. The most general duty of an heat exchanger in a process plant is to remove heat or add heat to the process fluid. If the exchanger is used for the purpose of removing heat from the fluid, it is called as cooler. If it is used for adding heat to the system, it is called as heater. Therefore, the word exchanger really applies to all types of equipment in which heat is exchanged, but is often used specifically to denote equipment in which heat is exchanged between two process streams. Then classification of heat exchangers. So heat exchangers are generally classified according to the process flow. According to the flow nature, it is classified into cross flow, parallel flow, and counter flow. In a cross flow heat exchanger, the hot fluid and the cold fluid, two streams are entering the heat exchanger perpendicular to one another. So in a parallel flow, hot fluid and cold fluids are flowing in the same direction. In a counter current, the fluids are flowing in the opposite direction. Therefore, the heat exchangers are classified into counter current, co-current, and cross flow according to the flow nature. So, according to the configuration of the heat exchanger, it is classified into cell and tube heat exchanger, double pipe heat exchanger, finned tube heat exchanger, plate type heat exchangers, etc. Then, these are the commonly used types of heat exchangers: double pipe heat exchanger, cell and tube heat exchangers, plate and frame exchangers, plate and fin exchangers, spiral heat exchangers, air-cooled coolers and condensers, direct contact cooling and quenching equipments, agitated vessels, and fired heaters. So out of this, double pipe heat exchangers plays a vital role in almost all the process industry. It is very easy to assemble, maintenance, everything. So after that, cell and tube heat exchangers are the most widely used heat exchangers in all the process industry, especially in refinery operations. So it is very easy to clean, easy to install, easy to fabricate. Then plate and frame heat exchangers are used for some special purposes fluids. So chillers and coolers, plate and frame heat exchangers are used. For food acid and food chemicals and other heat sensitive materials, plate and frame heat exchangers are most useful. So this is the example for cell and tube heat exchangers. So it contains one tube bundle. So this tube bundle is placed inside a cell. The cell is nothing but it is a cylindrical vessel. So in which a bundle of tube is arranged. So in each end of the cell there is a nozzle for inlet and outlet. Then double pipe heat exchanger. It is nothing but more than two pipes are placed inside a large pipe. Double pipe heat exchanger. In a double pipe heat exchanger, a pipe is placed inside another pipe. So it can be a straight pipe double pipe heat exchanger or U-tube double pipe heat exchangers. So in a U-tube heat exchangers, the both ends are welded with U-tube arrangements. The next, plate type heat exchangers. So in a plate type heat exchangers, the plates are placed inside two fluids. So the heat is transferred through the plate. The fluids are flowing in between the plates. So the large surface area is available to transfer heat from one fluid to another fluid. So the plate type heat exchangers are mostly used in chillers and refrigerators. Then parts of heat exchangers. So heat exchanger consists of a cell and a tube bundle, the nozzle for entering and leaving the fluid, then tube seat, baffles, tie rods. So this is the example for tube bundle. Tube bundle consists of large number of tubes welded on a plate, that is called a tube seat. So it consists of a baffles and a head. So double pipe. The thermal design consideration for a heat exchanger. So thermal design consideration consists of cell, tube pitch, tube layout and tube count, tube passes, number of passes, and the types of tube seat, baffles placed inside the tubes, fouling consideration, and selection of fluids for tube and cell side. So now let us see what is cell. Cell is nothing but it is a cylindrical vessel. It contains front and back header, and inside the cell two bundles are placed, and also it contains a nozzle for inlet and outlet. This is the example for tube seat and tube bundle. The tubes are welded on a tube seat. So the inside the bundle, so in between the tubes, baffle plates are welded to avoid vibration and also to provide strength to the tubes. So the tubes are welded on a tube seat in the both ends. Tube seat is nothing but it is a circular plate in which tubes are welded according to a standard layout. So the layers are classified into triangular pitch, rectangular square pitch and tilted square pitch. So the tubes are arranged in triangular manner or in a square manner and tilted square. So in between the tube bundle, baffles spacings are placed. So the baffles are classified into cut segmental baffle, disc and donut baffle and orifice baffles. The next we will discuss about the design procedure for heat exchangers. So when you are designing a heat exchanger, first you have to allocate the fluid to the cell side and tube side. So we have to select which fluid is passing through the tube side and which fluid is passing through the cell side. Then we have to define the duty, heat duty, where the heat is added to the fluid or removed from the fluid, how much heat is removed or added. That is heat duty we have to define. The next we have to collect the thermophysical properties of the fluid, example density, viscosity and thermal conductivity. The next, what is the type of heat exchanger, whether it is a cross flow or counter flow or co-current. Like that we have to decide the type of heat exchanger. The next, we have to assume the overall coefficient. We have to select the overall coefficient for the heat exchanger, for which we have to refer the Perry book. Then we have to calculate the temperature difference, log mean temperature difference, delta Tm. Then finally we can calculate the Q equal to UA delta T. This is the basic design equation used to calculate the heat load. Then next, after finding the heat load, we can find the heat transfer area. So Q equal to UA delta T, from which we can use the overall heat transfer coefficient. We are assuming delta T is the log mean temperature difference, Q is the heat load. So from which we can calculate the area of the heat exchanger A. Then we have to decide the heat exchanger layout, then calculate the individual coefficients. Then after calculating the individual coefficient for cell side and the tube side, then we can calculate the overall heat transfer coefficient. If the overall heat transfer coefficient calculated is matches with the assumed overall heat transfer coefficient, already we are assuming an overall heat transfer coefficient. If this value is deviates less than 30%, we can accept the design. If the deviation is more than 30%, we can go for assuming next another overall heat transfer coefficient. The next, fluid allocation. So what are the parameters to be considered while you are allocating a fluid to the cell side or tube side? When you are selecting the fluid for tube side, the corrosive fluids must be given preference to tube side, because if the fluids are corrosive, it may corrode the tubes. If the tubes are corroded, we can easily replace the tubes, or we can easily plug the tubes, and equally it is easy maintenance. But if the cells are corroded, it is very costly. Cells are very costly, expensive material. Almost it is made up of stainless steel. So corrosive fluids should be taken in the tube side because of easy maintenance and easy replacement of the tubes. Like that, the fluid which has the tendency to fouling, the fouling nature fluid also can be taken into the tube side. Then only we can easily remove the tubes or clean the tubes. Then high pressure fluids, toxic fluids, cooling water and hot fluid. These all are the fluids we should given preference to tube side. The next, cell side fluid, high viscous fluid, fluid with higher flow rate, and almost all the process fluids should be taken in the cell side. So if the high viscous fluid, the cell side we are placing the baffles and other arrangements. So therefore the viscous fluid can be selected in the cell side. Like this, high flow rate fluid and process fluid also taken in the cell side. Then next step, we have to calculate the heat load. Using the formula Q equal to UA delta T, we can calculate what is the heat to be removed or added to the system. So before going for calculation of Q, we need the value for U. So we have to assume the overall heat transfer coefficient. Overall heat transfer coefficient for a given cell side and tube side fluid. So using the Paris Chemical Engineers Handbook, this is the table available in the Paris book. So hot fluid is one side, cold fluid one side. For the given hot fluid and the cold fluid, we have to choose the value overall heat transfer coefficient we have to assume. The next, we can calculate the LMTD, log mean temperature difference, can be calculated by LMTD equal to delta T2 minus delta T1 divided by ln of delta T2 minus divided by T1. So using this formula, we can calculate the LMTD. So for calculating the LMTD, we have to assume the tentative number of cell and tube passes. So how many passes in the tube side and how many passes in the cell side, we have to assume. Then we have to refer the Perry 8th edition for LMTD correction factor. So the mean temperature difference is calculated using this formula. After calculating the LMTD, we have to apply the LMTD correction factor using the Perry's book. This is the chart for which we have to calculate the R value. R equal to T1 minus T2 divided by T2 minus T1. Then using this chart, we can calculate the LMTD correction factor F. Then after that, the corrected LMTD is calculated. Then apply the design equation. Find the area for heat transfer. The area for heat transfer is given as A equal to Q divided by U into delta Tm. So this is the area required to design a heat exchanger. So once the area is determined, then we have to calculate how many tubes are required to accommodate this area. So we have to decide the number of tubes. Before calculating the number of tubes, we have to assume the tube outer diameter, tube OD, and decide the tube layout, which type of layout, whether triangular pitch or square pitch or tilted square pitch, we have to decide. Then we have to decide the number of passes. Then refer the Perry book from table 11.2. Choose the tube thickness and tube ID. Then also we have to choose the length of the tube. The most commonly used length available in the market is 8 feet, 10 feet, 12 feet, 16 feet and 20 feet. So once you choose the length of the tube and select the diameter of OD, outer diameter of the tube, then we can calculate the wall thickness of the tube for a given Brigham wire gauge. If you choose 1 inch OD, 10 BWG, the thickness we can calculate. Like that we have to calculate the thickness of the tube. So once thickness is calculated, we can calculate the number of tubes using the formula NT equal to A divided by pi D into L. So A is the heat transfer area already calculated, pi is the value for 3.14, D is the diameter, nth is the L is the length. So number of tubes calculated, from which we can calculate the number of tubes per pass. So what is the tubes required for one pass? Then next we can go to the cell side dimensions. We can calculate the cell diameter. To calculate the cell diameter, we have to refer equation 11.7 from the Perry book. For a given triangular pitch, for a given layout, we have to choose the value for PB and PN. So here the triangular pitch is chosen. For a given triangular layout, tube pitch P dash equal to 1.25. The corresponding PB value and PN values are taken. So using this PB and PB value equation, using the equation 11.7, we can calculate the N value, N equal to, we calculate the C value. Then C equal to 0.75 D by D minus 36. So using this formula, we can calculate the cell side diameter, ds equal to D plus C. Here D is bundle OD, D is the tube outer diameter, C is we can calculate from the equation 11.7. So using this formula, cell diameter is calculated. Then after that, calculate the cell side Reynolds number. So cell side Reynolds number can be calculated. Then applying the cell side Reynolds number, the cell side heat transfer coefficient is calculated. So cell side heat transfer coefficient is Hs equal to H1 minus Jc, Hs equal to Hk, Jc, Jl, Jb and Jr. So this is the individual heat transfer, cell side heat transfer coefficient. The next we can calculate the overall heat transfer coefficient, 1 by U equal to, so 1 by Hw into Xd divided by Kw into D plus 1 by Hs. Using this formula, we can calculate the overall heat transfer coefficient. If this overall heat transfer coefficient is within this limit, less than 30%, we can accept the design. If it goes beyond 30%, we can reconsider the design. We have to assume another value for overall heat transfer coefficient. Then we have to repeat the design calculation. Thank you.